video is all about periodic trends or trends that change slowly as we go left to right or up and down the periodic table. So the first one is about atomic size, and this isn't about mass or the average atomic mass that you'll find on the periodic table. This is about the radius or the actual size or volume that the atom takes up. Like the picture shown here, what's the actual diameter or average radius of the atom? And so here's the general trend. And what we want to note first is that elements are the most stable with filled subshells. They want to meet the octet rule or get 8 outermost valence electrons, unless, of course, they're hydrogen that has 1 electron and wants to be like helium that only needs 2 electrons to fill its outermost energy level. But all the rest want to be like the noble gases and get to that magic 8 electrons to meet the octet rule. Okay, so what do we want to know about the size or radius of the atom? Well, as a general trend, going down the periodic table, atomic radius increases, so size increases, and going left to right, size decreases or gets smaller. So that's the general trend. If we wanted to write this right on our table, we'd say that radius, decreases. I worry about writing just size because so many folks confuse that with, mass, average atomic mass. And then here we have radius increases. And some people just, write arrows for that too. But radius decreases left to right and increases going down. Now, the thing about going down the periodic table is as you go down the periodic table, you add principal energy levels. So, if you want to just think about that Bohr model, you're adding a whole another ring to that Bohr model. That atom is getting bigger and bigger as you go from lithium down to sodium and potassium and rubidium. You're adding, a whole energy shell. And so most people are okay with knowing how that radius gets bigger going down. But why on earth does radius get smaller going left to right when you're adding protons and you're adding electrons and mass is going up? Really mass is going up left to right, but radius is decreasing. That's a lot trickier to wrap our mind around. So let's first look at hydrogen and helium in the first period. With hydrogen, you have 1 proton in the nucleus and 1 electron. You're at the first principal energy level. Now with helium, you're going to add another proton and another electron, and that electron is being added at the same energy level 1, and so there's this opposites attract or this pull that causes radial contraction going across from hydrogen to helium. Let's go to period 2. Let's add a whole nother shell. Well, that's why as we go down from hydrogen to lithium, we add a whole another energy level or shell. So radius gets bigger as we go down from hydrogen to lithium, down the alkali metal column. But as we go left to right, from lithium to beryllium, we add a proton in the nucleus, which helps pull or contract. It attracts those electrons at that same energy level. Go across to boron, even more contraction. Carbon, even more. So we're seeing this radial contraction because for every electron that we're adding at the same energy level, we're adding protons to pull that energy level in. And so go across to nitrogen, more pull, into oxygen, more pull, into fluorine, into neon, even more. And then we're going to go down to the next period or the next row. We're going to go to the third period at sodium. We add a whole nother energy level, so radius gets a lot bigger. But then as we go left to right, from sodium to magnesium to aluminum, we see that radial contraction going left to right. Silicon, phosphorus, sulfur, chlorine, and finally to argon. So going left to right, we get this radial contraction. Going down the group, of course, from hydrogen, get bigger at lithium, get bigger at sodium, get bigger at potassium. Every time we go down the group or family, going down the column, we add, principal energy levels. And so the radius keeps getting bigger. from helium, for example, go down to neon, go down to argon. And so our general trend was that atoms got, bigger going down, but smaller going left to right. So this next trend, ionization energy, follows it, but it's really the opposite. Ionization energy is the amount of energy required to remove the outermost electron, creating a cation. So it's really about how easily can we remove the outermost electron. Ionization energy decreases going down and it increases going left to right. Okay, so going left to right, ionization energy increases. And going down the table, ionization energy decreases. In other words, for those biggest atoms, they don't really notice if they lose that outermost electron. So really think of francium as your largest atom and helium up here as one of your tiniest atoms. Francium just does not notice if you pluck away or ionize or remove that last electron. Whereas a small atom like fluorine really is going to notice. It's going to take a lot of energy to remove fluorine's outermost electron, but it will not take much energy to remove francium's outermost electron or cesium's outermost electron. Okay, so the practice says, maybe we should clean this up a little bit. Put the following elements in order of increasing radius and increasing ionization energy. So we're going to put these, I'm going to actually do it up here. We're going to do radius and we're going to do ionization energy of these elements. It says increasing. So we're going to go smallest first to biggest. Okay, now remember, the biggest atoms are down here at francium and cesium. Okay, so if I want the biggest atoms from oxygen, barium, let's mark up oxygen right here. And we need aluminum, and we need neon, and we need barium. Okay, well, in terms of radius, barium is really big, and then we've got aluminum, and then we've got oxygen, and neon would be the smallest. So in terms of size, we've got neon, oxygen, aluminum, and barium. Now, ionization energy. It takes the most energy to remove an electron from the smallest element. So if the smallest element is neon, that is going to take the most energy to ionize. Noble gases really don't want to be ionized. And then we'll have oxygen, and then we'll have aluminum, and then we'll have barium. So barium is really big, like cesium or francium. It's not really going to take much energy to ionize it. So small ionization energy for a big atom, and big ionization energy for a small atom. So these trends are really opposites. Okay, so this concludes periodic trends.